Hello everyone, welcome to the fourth episode of the LLM show. I'm your host Shamain Siri. So this episode is an extension of our previous episode where we discuss about the concept of parameter efficient fine-tuning methods in relation to the Hugging Face Falcon block. So the episode number 4 focuses on QLoRa, which is the latest parameter efficient fine-tuning algorithm in the town. We will also dive deep into the core concepts of QLoRa, covering things like low rank adapters as well as normal 4-bit quantization. And finally, we will go through the Hugging Face notebook on how to fine tune a Falcon 7 billion model with the QLoRa method. Yeah, let's when you're talking about LoRa comes from this family of parameter efficient fine tuning methods. So people have been working on this since I would say like 2019 or 2020. There's a huge research community for this. Yes, I'm not going to go through the LoRa paper, but I found this amazing blog post of summarizing LoRa from the PyTorch Lightning crew. So I will share that, and I have found several hidden gem videos for LoRa and QLoRa, like in YouTube. So in the description, I will put the links to them. So if anyone wants to dive deep into these papers and understand everything behind it, they can surely kind of go through these videos as well, because these videos are really good, man. Like I learned a lot about LoRa and QLoRa. So this is like the like PyTorch Lightning blog post, parameter efficient LLM fine tuning with low rank adapters. Um, so basically, they also say like why these parameter efficient methods are important, which is pretty common. And then so they say we discussed fine tuning allows us to adapt a model to target domain and target task. Still it can be computationally very costly. So basically there's another blog post if you want to like kind of understand about those adapters I was mentioning about, other adapters and all,
Mm, mm,
like prompt tuning and everything.
prefix tuning. Yeah.
Yeah, they have this previous blog post where you kind of can know all about this theory, and they have also cited all the papers, which is a pretty good thing. I actually read about it. But today's thing, because we need to know about LoRa, because QLoRa has used LoRa. I like the name though. What is LoRa? How does it work? So first thing is, this has a lot to do with like metrics decomposition. So the
Oh,
idea is any higher rank metrics kind of can be represented with a low rank matrix. So if there are like kind of repetitive patterns and all, right, that's the idea of
yeah.
matrix decomposition. So mm, but LoRa is a bit different. So they are not saying, hey, we there's this large language model, right, with 65 billion or 40 billion parameters. We can kind of represent that 40 billion parameter model with maybe 1024 parameters or something. It's not what they say, but what they're saying is the gradient metric. We can think the gradients, right? When it comes to backpropagation, we can think the gradients of a metric, sorry, gradient of an LLM as a huge metric, right?
Yeah.
We can think that way, like it's a huge matrix. And what they are saying is that huge gradient matrix kind of can be presented with a low rank matrix. So that's the idea. Is it
Represented
clear?
as a low rank matrix. Yeah.
Yeah. Mm,
So
and
in
the
the
other,
the gradient matrix is usually, is there any easy way to visualize the gradient matrix?
uh, I mean, gradient matrix is same as the weight matrix, right?
Yeah. Yeah.
Because
So each weight has a
for
gradient.
each weight, so weight matrix is like it could be a huge matrix, right? I mean, we can think of it as a huge matrix, like all these layer weights and all. I mean, go back to good old day back propagation. It just it's just the same, so the one good thing is LoRa. So there should be a lot of theory. I kind of read it. So what they're saying is, you it's like you kind of can move this optimization thing from, maybe like they are comparing a case of three-dimensional case. You can still get the like kind of almost the same results with by moving it to a two-dimensional plane kind of a thing. But yeah, but what they say is, we don't like directly decompose the metric, right? We don't directly, what they say is, we don't directly decompose the matrices, but what we do is we will learn this new decomposed matrix. That's
Yep.
what they say, they are like, we are going to learn this decomposed matrices via backpropagation. So this is something you need to understand. So you kind of, the other way, the idea is like, there's this big gradient matrix, and you need that big gradient matrix to kind of update your parameters. That's what the fine tuning is, right? But that big matrix kind of can be uh, decomposed into a smaller one. So basically that means we need to have smaller number of new trainable layers, because these weights, like weights of the LLM, have already trained with large amount of data. So that's the
Yep.
idea. So yeah, we are going back to good old day back propagation and gradient updates. So this is delta W, right? This is
Is
like
there
the learning
learning?
rate.
Yeah.
So you can write, you can kind of visualize the gradient update like this, right? Weight
Yep.
matrix plus weight matrix equals weight matrix plus delta W. Okay.
Yep.
So, and then there's a good thing. So what they say is, so usually how we write our output is updated metrics into the whatever the input, right? X, you have
Mm.
the updated
Yep.
weight matrix into
Yep.
the X. So what they do is, they write the matrix like H equals the output equals WX into
Plus.
delta WX, the gradients, which
Yep.
is pretty much normal thing, right? And the nice part is, now this part is frozen.
Yeah.
The W part is frozen, and only delta W being computed. And for these delta Ws, we have, like, for what we are calculating these delta Ws, that's the decomposed metric. That means these newly injected LoRa layers. Okay.
Yeah.
So
This is like
uh,
ResNet as well, right? With the
yeah, exactly.
high.
Yeah, this is just like, this block is really nice, man. I really like this kind of stuff. So just helping to summarize everything. So input, pretrain weights, embedding, and then this is a regular fine tuning. You update all your weights, and then you take the input and send the updated weights. Sorry, take the input and send through these updated weights and get the output. And they are saying this is actually the same, but that's what they say. So these are the pre-trained weights, these are the updated weights. Sorry, this is the weight update, which is like
Yep.
delta W, and you can send the input with them and kind of concatenate them, and still you get the same thing. So this one and this one is almost same, right?
Mm-hmm. Mm-hmm.
Now they only talk about this matrix. So what
Yep.
they say is, this matrix, you don't need all these 65 billion weight updates. You kind of can represent it with a smaller one, right? That's pretty much LoRa is. And so when we train fully connected layers in a neural network, as shown above, the weights matrices usually have full rank, which is a technical term meaning that matrix does not have any linearly dependent rows or columns. Which this is true, right? So what they're saying is like, if we just think of the pre-trained weights, we just can't decompose them into uh, into a lower metrics, because most of I mean almost mm, all these weights are unique, kind of these
Not
rows
random.
and
Yeah.
columns, they are
Yeah.
unique, and that's the weight metrics. But it's what they're saying is for the gradients it's not the same. While the
Okay.
weights of the pre-trained model have full rank on the pre-trained task, the LoRa authors point out that pre-trained large language model have a low dimension, thank you,
To a
which
new
they
task.
are adapted to a
When?
new task. So basically, you get the idea, right? This is what the theory is if you want to go through the maths. So I kind of like the way they have used it, but in implementation wise, this is so easy. Um, yeah. So now they say like what is happening in this like decomposed delta w, what is happening, how we kind of decompose this and kind of merge it with a normal neural network and do the fine tuning. um, so basically what they say is like keep the w frozen, which is the original weights of the large language model,
Yeah.
and only train new WA and WB. Let's see what is this WA and WB. So basically, WA and WB are like this autoencoder.
Yeah.
You first take the input.
Or linear.
No,
Yeah.
yeah,
Yeah.
it is. Yeah, it should be right, because they do apply this
Yeah.
for attention layers and fully connected layers,
Yeah.
attention heads. So we'll touch that part, but the idea is like you have kind of WA
Yeah.
is an A into R dimensional matrix,
Yeah.
and then WB is R into B
Yeah.
dimensional matrix.
Yeah.
Why? But you can think of this as an autoencoder. So the idea is you have these new layers. What they do is they transform your input into low dimensional space, and then from low dimensional space again you transform back into high dimensional space and interpolate with the output from this frozen layers and keep doing so. This image explains all. So do you understand what they are doing?
WA
This
and WB untrainable. Yeah.
Yeah.
And then
So
R is a smaller number than A and B.
exactly, yeah. I mean, why they have used R is so you can reduce the parameters by a huge margin. Yeah, this is pretty much adapters. And again, if you want to know the maths and all, I
What's
would
R
highly.
normally? It says
Sorry.
choosing the rank is the next topic.
Yeah,
What
yeah,
is
it's,
R
it's
normally? It's like
so it's like I've seen it's sometimes even low as 64.
mm,
Yeah,
okay.
it's crazy, right? Like you have a like billion parameter model, and you kind of can adapt this to a custom task by adding little amount of parameter. There's a big
64 for
model.
each
Yeah, you
multi-head
use
attention
lot of
or something.
like LoRa layers,
Yeah.
LoRa weights. They say LoRa weights. You can use it in between different. I mean, It's also. It will also get squashed into your design choice, so you can add these weights in several parts. That's pretty much it. So yeah, that's pretty much LoRa. So then choosing the rank. So rank is a hyperparameter. So smaller the R, so you can see you will have less trainable parameters, right?
Mm-hmm.
And yeah, that's pretty much it from here. And yeah, we this is just the implementation part, which is pretty easy, right?
Mm-hmm.
So the only difference is like this is a matmul, right? Like X, you have W is like pretty much the frozen weights,
Yeah.
and WA is more like the, I would say, the encoder of the autoencoder part, like which squashes the input, and then WB is like which again that WB
Mhm.
is the one that upscales, right? So
Yeah.
So basically, what they say is,
And alpha is the learning rate, I guess.
so no, but what they say is, use scale. So what they're saying is, no, this is not learning rate. Like, this is more like
What is alpha?
a scaled LoRa weights.
Uh,
So it's a scaling
W
factor.
and WV.
So
Okay.
the
Why don't
first
they?
line you get it right. First line
Yes,
you
yes.
compute, you
Second
run
line I
you
get except the alpha. Where does the alpha come from?
yeah. So what they're saying is, alpha is a like a hyperparameter, so this is like a scaling factor, like softmax
Yeah.
temperature or something. It's like a scaling thingy. You can
Mm.
kind of scale this part,
Oh,
like
by default, alpha usually set to 1. Okay.
yeah,
Which is, I
in
mean,
the
I thought alpha was more like learning, right? Which is fine,
uh,
I guess.
yeah, I
Okay.
mean,
Seems
because
big, but okay.
yeah, what I mean, what we need to think is, when it comes to the back proper, because this is the forward pass, right?
Oh, okay.
So
Yeah. Yeah. Yeah.
this is
Yeah.
the,
Yeah.
come on, man, we are using AutoCAD. So this is the forward pass, and in the backward pass, it's such a good thing is, you don't need to come up with a different optimization. You can still use Adam W or whatever it is,
Hmm.
because it's just like weights, just a
Yeah.
thingy. So in the pseudocode above, alpha is a scaling factor that adjusts the magnitude of combined result. So then they talk about parameter efficiency and all, which is like pretty normal. I mean, you guys can go through it. Uh, and here are a few tips. Remember, we talk about this, Ravindu, like they say, when it comes to inference, now the good
Yeah.
part is, this is really good for the industry. So you can understand where we can kind of train several LoRa models, right? We
Yeah.
can train several LoRa models with this big
Hmm.
um, W, which
Oh,
is
yeah.
like the frozen LLM weights. So what they
Yeah.
say is, then you can kind of save it separately.
Hmm.
You can compute whatever it is, and then use these adapter weights.
Yeah.
um, yeah, but I would say it would still need some kind of engineering work, right? To kind of, because these, we will input a lot of layers for a single task in between.
But Hugging
It-
Face abstracts away everything.
yeah, exactly, yeah. So the yeah, of course, when you're using Hugging Face, it's easy. So the idea is like, so there's this nice thing. um if you have different clients, if you
Yeah.
have different clients, we kind of can use it, you kind of can use it
Use the
for
same LLM. Like,
yeah,
yeah.
that's pretty cool. um
Yeah. So the code will be relatively simple as well.
yeah,
As in,
exactly. Yeah, this is just amazing. And wow, LoRa weights can be small as 8 megabytes if we choose a rank of R8. This is
mhm.
amazing, man. Like 7 billion. There's like, you have a
Yeah,
model with
but it,
23 gig,
yeah.
and you only fine tune part of it. That part is just 8 megabytes. Still, you kind of can get better results.
Yeah.
Mm,
Yeah.
yeah, I wonder why people don't use this for Bert and Roberta when it comes to computational cost. But I've seen papers doing so.
What
I mean,
is
initially,
do you say Bert and Robert are still
Robert.
relevant? Like, what do people
Yeah,
use?
because I saw the initial papers about adapters. They have
Yeah.
used these bird things, Bert and Robert, and normal language models to prove their concept, but maybe not good as this, because the idea is, large language models have a lot of knowledge in them, right?
Yeah.
Already. So basically, it's more like extracting what we need. So yeah, that is my adapters, and this is the important thing. Why LoRa? Why not other adapters? So simple. They say like LoRa performs better compared to other parameter efficient methods like adapters, prompt tuning, or prefix tuning, right?
Yeah.
So that's why we are using. So this is pretty much LoRa. So you can see LoRa works better with GPT-3 for different tasks. And this from the paper. And I highly encourage you to read about LoRa paper. So yeah, then we are gonna go to the final part, which is QLoRa. So QLoRa is using LoRa, but their point is, oh, still this would take a lot of memory. At least still this would take a lot of GPUs, because of course we are only fine tuning small amount of parameters, but still in order to fine tune these parameters we need to get outputs from in between layers in the large LLM, right? So
Hmm.
you need to compute this stuff.
Yeah, you can do it in the CPU, but that'll be very slow.
Yes, exactly. So that's the catch, right? Then it would take a lot of time to
Yeah,
train. That also will be a problem, especially if you're working on things like recommendations and e-commerce. You kind of need to train your models like every now and then, like it's like every day or every 3 days, whatever it is. I mean,
yeah,
it's like you need to keep doing that. So
yeah.
it's hard. So Kevlar is more like, hey, we will work work on the memory part. We'll come up with a method so you can kind of reduce the size of this big model. Still, you can kind of get the best results. So that is pretty much the QLoRa part. This is QLoRa, efficient fine tuning of quantized LLM. So quantization, you did electronic and electrical, right? Yeah. So
Hmm.
we had a lot of quantization stuff, right? Voltages and all. Remember
Analog to
back in the
digital
day?
converters, you mean? Or
Yes, yes, yes. It's like quantization was a thing those days. So yeah, honestly, I didn't like electrical engineering at all back then. So I had to kind of refresh my memory once I started, my deep learning journey around this paper.
yeah.
Uh, you kind of, I mean, just in layman terms, if you want to like understand everything, you need to have some knowledge about quantization,
Hmm.
and also you need to have some knowledge about adapters. So we know adapters, right? So it's pretty cool. Pass,
The
but yeah,
basic idea is basically that you don't need the numbers to be that precise when
exactly.
you're for deep
Yes.
learning stuff.
Yeah. Yeah. Yeah, as I mentioned before, you kind of this paper is all about quantization and adapters. We will talk about quantization, but we already have discussed adapters, and it is pretty much the knowledge you need to know. Like basically what they do is they have just used adapters as is, but they came up with a quantization method. So this is the paper, Clora efficient fine tuning of quantized LLM. So University of Washington, and kudos to all these authors. I think this is the guy who has open source Bit and Bytes, right?
You said
Yes.
Tim? It might be
Yeah.
the same Tim.
Yeah. He's the one. Thank you very much. And maybe he saved a lot of machine learning engineers. uh, so it's not APIs only. So yeah, let's go with the abstract. So we present QLoRa, um, an efficient fine-tuning approach that reduces memory usage enough to fine-tune 65 billion parameter model on a single 48 GB GPU. So basically, this is not the Falcon model. This is the Llama from Meta, right? So it's
Hmm.
65 billion model. They have only used single 48 GB model to fine tune, which is pretty awesome. Like this is again, we can build a lot of stuff, right? Like
Hmm.
this, if this is, if this works, and it is working. Um, and the next part is, it's not just like they are getting competitive performance, but they still can get the same performance as 16-bit fine tune, which is awesome. Like
Hmm.
that means this is a powerful technique. Um, so QLoRa backpropagates gradients through a frozen 4-bit quantized pre-trained language model into LoRa. So the idea is LoRa is there. I think I read this paper just to give you some idea. So they keep the LoRa in full precision, LoRa layers, and then they sort of freeze the model, freeze the LLM model, in 4-bit precision.
Yeah.
That's
Yeah.
the idea.
Because LoRa,
And
yeah, if LoRa needs only 64 megabytes or whatever, then it's
exactly,
definitely
that's the part.
not a problem.
Yeah. And then they say like here they say like they have achieved really good results compared to ChatGPT, and just training it 24 hours, training for 24 hours on a single GPU. That's pretty much it. And this is also an important part. So in this paper they introduce a new quantization method, and that quantization method with that quantization method they kind of introduce a new data type, which is 4-bit normal float.
Mm.
So this is like a new data type they used. So this is not just like 4-bit quantization. We'll get into it. It is really interesting, really.
Yeah.
I kind of I really loved that part. And then they also do this double quantization to reduce the average memory footprint by quantizing the quantization constant. Uh,
What is the quantization constant?
because you remember, like, if once in you do, if you remember the mixed precision training, when
Mm-hmm.
you quantize something,
Yeah.
but you can always keep the quantization constant, and then you kind of can dequantize it. There will be still an error,
Mm-hmm. Yeah.
like, but it's like you have a value, now you
Yeah.
squash it, and you
Yeah.
say you kind of do just before doing the update or something, or maybe after the update, then you multiply it by that constant that
Yeah.
you squash, so you kind of can get
Oh,
a
okay.
closer value. Go through it.
Yeah.
So, and then they have used something called page optimize to manage memory spike. I kind of read this because I'm not a pro in GPU architectures, but
Mm-hmm.
the idea is like what they're saying is when they're trying to dequantize this, there could be these out of memory errors, and
Yeah.
there would, because if the problem with out of memory errors or spikes uh, in deep learning is if it happens in the middle of the training, everything will go down, right? It can't recover. So I think they have come up with a method like this page optimizers, and what they say is they even see they even they have code open source as well as CUDA kernels for bit training. um, yeah. So that's pretty much it. Then they also say about their like what how the results and all. But I mean, this paper came, I think, after the PEF library, after Hugging Face. I mean, the idea is like nowadays these papers they are like they really wanna like open source the code first,
Mm-hmm.
because of the effectivity and because of the hype right now we have. So we all know this is working because Hugging Face has an official blog. That means, yeah, it is working pretty much. It is engineering friendly as well. But the main idea of this quick walkthrough is to kind of understand the concepts. Yeah.
Mm-hmm.
So in the introduction, again, like they say, Ravind, you ask how many how much
780 GB.
GPUs you need, right? GPU memory. So, however, fine-tuning very large language models is prohibitively expensive. Regular 16-bit fine-tuning of a Llama 65 billion parameter model requires more than 780 billion GPU memory.
Mm-hmm. Is there any model or any GPU that has 780 GB?
No, 780 GB
Yeah.
GPU memory, not billion. I'm crazy. So I don't think so. I don't think so. So the idea is, imagine if you take, I mean, you first need to fit the model, right?
Yeah.
And then definitely, if you don't have a custom server or something, you need to go with model parallelism. As far as I know, it's
Mm-hmm.
not that easy task. It's not like data parallelism. There are so many methods to kind of distribute your layers and all,
Mm-hmm.
so that could add a lot of training time overhead. I would say because of that,
Yeah. There's
these people
communication
should
overhead as well.
have, yes,
Yeah.
yes, these people should have their custom servers. That's what I
Yeah.
think, at least. Yeah, I mean it's something. Anyway, it's big, like 780. Um, and yeah, techniques only work for inference and breakdown during training. So basically, what they say is these quantization methods can reduce the memory footprint. So I guess this memory footprint is more like remember like you can easily quantize it for 4-bit or 8-bit or something, right?
Yeah.
With that bit and bytes. So what they're saying is that's a way. That's a way to do it. You can
Yeah.
kind of quantize your LLM and use it
Yeah.
for custom tasks only for inference. But when
Yeah.
it comes to fine tuning, it would break. I mean, even in inference, some it might reduce performances. I mean, that's what I think. But maybe for some tasks, you might not need the full precision, right?
Yeah.
Because if you take a large language model, it has seen a lot of data, right? It is a well generalized model, but for your own task it might not be a big problem. And we demonstrate for the first time that it is possible to fine tune a quantized 4-bit model without any performance degradation. So this is huge, man. Like literally, that means like you can just squash and you can do the thing, and so the idea is again to wrap this up. You first convert your checkpoint into 4 bits and then you use learnable or low rank adapters. Is it clear or you have any things there?
No,
Sure.
straightforward, I think,
Yeah.
at the moment.
Mm, so again, they are saying like, hey, we were able to fine tune 65 billion parameter model that that used to have 160 gig, 100, sorry, 780 gig GPU memory. Now we only need 48 gigs, which is
Yeah.
pretty cool. And then now so what they're saying is now the largest publicly available model to date, fine tunable on single GPU. So what they're saying is because I think Llama is the largest publicly available checkpoint, and now
Yeah.
they can train it with just a single GPU. That's pretty much it, and also
What is the Guanaco model again?
I think that's their name. Like, Guna. I don't ask me why they have used this name. I have seen that it's like Gunaka Gunako family of models. So yeah, it's the name of the model because it
Yeah.
was somewhere in the see we our best model family which we named Guanaco. Is it
Okay.
like
Okay. Yeah. Yeah. So
something Spanish or something? I don't know.
generative universal assistant for natural language adaptive context aware omnilingual outputs.
So
It's an animal
you know, okay,
Yeah.
it's an animal. What
Yeah.
type of an animal?
Species of mammal is a camelid native to South America, closely related to the llama.
Okay, nice. They have like see they have different
65,
models,
33.
65
Yeah.
billion, 33 billion, and see these are like 13 billion model, or you only need
10 billion.
10
Oh, 10
gigabytes.
GB. Yeah.
Yeah, I would say this is the GPU memory.
Yeah.
Yeah, so
Which
that's
is
pretty
better than
much.
BUD.
Yeah, because yeah, Bart can't, right? This is like the hard part to understand. I mean, I kind of had to go through this several times to get the idea, and I also found an amazing YouTube video for this. I will kind of put the link. It's just so good. The person has explained it really well, and I actually took a page out of him. So, so then they have come up with this new thing called 4-bit normal float, right?
Mm.
So what they say is like it's been theoretically proven that um, optimal quantization data type for normally distributed data that yields a better empirical results than 4-bit integers and 4-bit floats. The idea is, so there are 4-bit integers and 4-bit floats, right? What they say is we are using this. We kind of think your weight set is kind of normally distributed. So we create this new quantization method where we call it like 4-bit normal float, and they say information theoretically it is the optimal quantization for data with a normal distribution. So and then double quantization is the quantizing the quantization constant to save bit of memory, and the page optimizers using NVIDIA unified memory to avoid gradient checkpointing memory spikes that occur when uh, processing a mini batch with a long sequence length. Have you heard of gradient checkpointing?
Is that different from normal checkpointing?
Yes. Gradient checkpoint, right? So the idea of gradient checkpointing is, I mean, when we are kind of when we are kind of we need to compute gradients for all layers, right? When
Yeah.
to do the back propagation, so then we need to use chain rule, and
Mm-hmm.
then the idea is like, in order to compute chain rules,
Mm-hmm.
I mean, we need to have activations as well, the forward values as well, to
Yeah.
compute the chain rule.
Yeah. Yeah.
So the
Yeah.
idea is like you can't keep all these activations. It's like a method why to keep all the activations in the memory, but to kind of store them,
Mm-hmm.
but to kind of store them and use it when you are computing the gradients. But yeah, then again there will be a trade-off between the speed and the memory, which is kind of pretty common. So yeah, um, so let's kind of wrap this up to understand what they're doing. Again, the VI is still in the introduction, don't worry. So there are some other insights as well. This is interesting. We highlight then model-based evaluation while providing a cheap alternative to human annotation. So like use ChatGPT to evaluate your things rather than using
Mm-hmm.
whatever the MTurk or something. That's what they say. I don't know. So yeah, now it's pretty much we are done, and now they kind of give an overview of their paper. Again, this image is really good. So the idea is this is the normal fine tuning. So you have the 16-bit transformer, and this is the optimizer state. Do you remember like how Adam works? Like we need to keep these gradients and everything in memory, right? Like,
Yes.
and also we
LB
need to,
or something.
yeah. I think
Ethan.
also the deviation and this running averages as well.
Mm-hmm.
So yeah, we need to kind of keep them, and so that's why sometimes people wonder like why for fine tuning it takes very little amount of memory, but for training it takes a lot. Because you need to maintain some kind of a state, right, for every parameter. So basically there could be maybe like 3 times of your parameters, like what they
Mm-hmm.
take actually, because that's why. So what LoRa does is LoRa chunk down this big optimizer state into smaller things, because we are only injecting few amount of layers, right? Do you understand this? I
Okay,
really
so
like
for
this.
each, there's a different optimizer state for each multi-headed tension block or whatever it is.
No, 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 not like that. This is more of a figurative thing. What they say is,
Mm-hmm.
so if you don't use LoRa, your
Yeah.
optimizer state is huge, right? Because you
Yeah.
are you are trying to compute gradients for each and everything.
Okay. Yeah. Yeah.
But when you are using LoRa, it gets chunked down into these layers.
Because
In
they're
a way, they are
tiny.
like they are independent. That's what they say, LoRa blocks,
Mm-hmm.
right? Like you inject them. It is not entirely independent. They can be dependent, but the gradients will
But I
propagate
mean, it'll
through
be much smaller. Yeah.
exactly much smaller states. And the QLoRa is um, not only you um, not only you kind of downscale your
Yeah.
transformer, so less memory, and you also use lower blocks, and also you kind of use this gradient checkpoint in this page optimizer thing. So
Mm-hmm.
they have found another way in
CPU checkpointing or something.
yeah.
Right.
We go to you asked me what is a quantization constant, right? So
Yeah.
what they say is, so basically this is like, we don't need to go through everything, but just to summarize, quantization is the process of discretizing discretizing an input from a representation that holds more information to a representation with less information, right? So basically
Hmm.
you
Compression.
reduce the precision,
Yeah.
but then you also can reduce the size. That's the idea.
Mm-hmm.
So now this is, we are going to good all day quantization. So imagine uh, if you want to quantize 32-bit, like float 32-bit thing
Yeah.
to int 8 tensor.
Yeah.
So
Yeah.
int 8 ranges from minus
Yeah.
127 to plus 127,
Yeah.
right?
Yeah.
I guess 256 values, right?
It's two five
But
six. If it's unsigned, it's 256. But
if
if
it's
it's
signed,
signed,
it's
it's
255.
-17 to 127.
Yeah, okay. So how you do this is, so this is the quantization construct. I have this math part written down. The idea is like,
Yeah.
given a float 32 vector, you take what is the max in it. That's what you do. You know,
Yeah. Yeah.
like you read some kind of a voltage, something like that. You read something here, like in your, maybe just
Hmm.
imagine there's a weight
Is
vector,
that the
right?
theoretical maximum or the
No, no, no.
the
What
actual
you,
maximum
yeah,
that is there?
actual
Okay. Yeah.
maximum of what you have.
Yeah.
So
Yeah.
imagine you have weight vector with five
Yeah.
things,
Yeah.
2, 5, 10,000 or something. Then
Yeah. Yeah.
absolute maximum
10,000.
is 10,000, right?
Yeah. Yeah.
Then you then you divide 127 by 10,000,
Yeah.
and this is like this constant, and then you multiply it with that value, because that is the maximum value you can get, right?
Mm-hmm.
And then because if this is imagine if this is 127,
Mm-hmm.
then it's like
Okay.
pretty much you can make it, because you can show 127 8-bit int.
Those are
Because,
vectors, right? Yeah.
yes, and yeah, so this is the constant, and basically you need this to dequantize, so you kind of can dequantize this as well. So this is like the normal way of quantizing anything, I think this is what uh, bits and bytes been doing. But what this QLoRa says is,
Where does the C come from? I still don't.
c
Oh,
c
yeah,
is
yeah. C
c
is
is
the
for this part.
127 divided by, okay, max. Yeah.
Exactly,
Okay.
exactly,
Okay.
yeah.
Yeah. Yeah.
Then the nice part is, if this vector has an outlier, imagine 20,000 or something,
Yeah.
what happens is almost all values um,
Zero.
will be like zero. So
Yeah.
then you are not representing it really well.
Yeah.
So so then basically, in order to counter this property, they came up with this n float thingy,
Mm-hmm.
normal float thingy. So we'll do that. So mm, so they kind of mention like what they do. They what they're saying is, if we kind of can quantize in a better way that has some sort of an idea about the distribution of the weights. So basically,
Mm-hmm.
this would happen, right? There's no outliers, like the distribution. But then
Yeah.
what they're saying is, we also need to uh, come up with a practical method to quantize, because there might be different ways to quantize, but it should be fast and easy. So,
Yeah.
and
We
we
got
will
it.
show. So then again, they also talk about low rank adapters, which is pretty much what we talk. This is like hex, L1, L2, autoencoder weights. This is like the scaling factor. And then another good thing, memory requirement for parameter efficient fine tuning. So here what they have mentioned is, adding LoRa parameter, adding more LoRa layers or something doesn't hurt much, because the
Mm-hmm.
memory footprint is pretty less. It is pretty
Yeah.
less, right?
Yeah. Yeah.
So what they're saying is, the problem is not with LoRa or anything, but it's the problem is this model is enormous. If we can
Yeah.
squash it, it is good. And also
Yeah.
there's same with gradient checkpointing, basically keeping some activations, save them, and kind of moving from CPU. That figure showed that, right?
Yeah.
So it's like they're saying like so LoRa input gradients have a memory footprint of 567 megabytes, while LoRa parameters take up to only 26 megabytes. So with gradient checkpointing, the input gradients reduce to an average of 18 megabytes per sequence,
Mm.
making them more memory intensive than all uh, LoRa weights combined. In comparison, um, 4-bit base model consumes 5048 megabytes of memory. This highlights that gradient checkpointing is important, but also that aggressively reducing the amount of LoRa parameters yield only minor memory benefits. So
Mm-hmm.
what they're saying is, even though we don't train this
Yeah.
model, model has a lot of parameters, and they would take this amount of megabytes, and LoRa anyway. If when we are using gradient checkpointing as well, LoRa doesn't add much, right? What they're saying is, as far as I understand, so it's okay to have more LoRa layers. Am I understanding correctly?
Yeah, I think so. The model basically saying the model is the one that takes a huge chunk, and then the LoRa is like almost nothing.
And also they're saying like it is crucial for recovering full 16-bit precision. So I would say in future when we are training this would be a huge hyperparameter. How many LoRa adapters to use? I would say like people
It
would
should be the
use like,
max.
yeah, like whatever it fits, right, to your
Mm. Yep.
GPU. If you, as long as you don't, like batch size, right, as long as you don't overflow your memory, you can use as much as. So yeah, now that's been done, and now let's come to um, QLoRa fine tuning. So so basically QLoRa achieves high fidelity 4-bit fine tuning. We have two techniques we propose: 4-bit normal float and the double quantization. Additionally, we introduce page optimizer. So in QLoRa, they have two data types. Really. Like it's so important to
Mm.
understand low precision storage data type, which is like
Mm.
this 4-bit normal thingy.
Yeah.
Um, and
And one
so store,
computation
I
data
I
type.
would say
Okay.
storage is like the parameters, right, of the LLM.
Yep.
And then computational data type is like a brain float 60. So how I understood about this is, so basically computation type means they, so you need to get outputs from because you are injecting LoRa layers in between the LLM, right?
Yeah.
And then before some outputs kind of pass LoRa layers, they will kind of get generated via the parameters of the LLM, right? So what
Mm-hmm.
they're saying is, during the computation, they are using
Mm-hmm.
float 16. That's why we need to have a dequantization constant. You know?
Mm-hmm.
Do you get what I'm saying?
Not really, but just say it again.
Yeah. They have a storage data. That means they keep the checkpoint in 4
Mm-hmm.
bits,
Mm-hmm.
right?
Yeah.
And mm, uh, then imagine like so input to the LoRa layers, like just generated from some kind of a hidden layer in the like LLM, right? Because you let's say you inject LoRa layers in between attentions, right?
Yeah.
So so that input to that LoRa layer has to pass many layers of the LLM.
Mm-hmm.
Do you understand that part?
Mm-hmm.
And then that LLM is in 4-bit, right?
Yeah.
And But the thing is, you can't do computations in 4 bits and 32 bits because they are
Okay, yeah.
keeping 4 bits and 16
16
B
bit.
float,
Yeah, yeah,
because they are keeping LoRa layers in 16
yeah,
B float, you know,
yeah, yeah,
B float 16. So
yeah, yeah,
basically, what they say is during the computation time,
yeah,
they dequantize those values back
yeah.
into
Okay, yeah.
uh, like B float
B
16.
float 16. Yeah, yeah.
So,
Okay,
but
I
they are not,
understand.
they don't store that. That's
Yeah,
why. That's
yeah,
why this is efficient, and also
yeah,
that's why this can achieve better results than just quantizing. And
yeah,
also
yeah,
their quantization method itself is also good, you know.
yeah, yeah.
Yeah, so you can see like it's pretty simple. We dequantize the tensor to B float 16 and then perform a matrix multiplication in 16-bit. That means if
Mm-hmm.
there's if there are any metric multiplications or any operation, right,
Yeah, yeah.
you will quickly convert that 4-bit values to
16 bit. Yeah,
bfloat 16 and
yeah,
do it, you know.
yeah, yeah.
And that's why they are so skeptical about 4-bit quantization method, because if the quantization is a problem, they would never able to recover this, and they can't dequantize, right?
Mm-hmm.
So that would add a lot of quantization error.
Mm-hmm.
So um, and yeah, so this is like the core of the thing. Like it took some time for me to understand this thing, but the idea is like kind of simple. So their assumption is uh, pre-trained neural network weights usually have a zero centered normal distribution with standard deviation sigma, right?
Yeah.
So I mean, I kind of further understood about this concept from a YouTube video. I'll definitely put that link there in the description. So what they say is like so once you think there's a normal distribution, you can easily kind of unit normalize it. Like you can kind of set the range between -1 and +1, right? Because
Mm-hmm.
it's like
This is not
normalizing, like batch normalizing. So so we had
min-max
so many
scaling.
normalization methods. Now this is more like a weight normalization
Mm-hmm.
in deep learning. And then what they say is like so float for like 4 bits means like you can have 16 values, right? 2 to the power 4. So basically somehow they chunk this normally distributed data
Mm-hmm.
into kind of equal blocks of 16, and then quantize each
Quantiles.
block separately.
Mm-hmm.
um, I know this is a lot,
For each
but
quantile, how many quantiles?
so
Quantiles.
16, right?
16
Because
quantiles. Okay, yeah,
it's
yeah.
4 bits, right?
Okay.
And but this 16, the range, like, because one bucket has now set of values, right?
Yeah,
Then you can quantize those buckets. You kind of compute the quantization constant for that bucket.
yeah, yeah. Okay.
So you will have 16 quantization constant. So
Mm-hmm.
yeah, I'll quickly show what is happening there. Imagine you have a weight vector, right?
Yeah.
So this is my 0.01 minus 0.3, uh, 0.12, 10,
1.2. Yeah.
yeah,
20,000.
1.2, 10, 20,000, and 100, right? So
Yeah.
this is
Yeah.
like your weight matrix, think like that.
Yeah. Yeah.
So if you want to quantize this normally for 8 bits, remember that example?
Mm-hmm. Yeah.
So the idea is like now you need to compute the quantization constant, right?
Yeah. Yeah.
And then that constant is 0.00635.
Yeah. Yeah.
And then what you need to do is you need to multiply mm, this this constant by these values, you know,
Yeah. Yeah.
these real float values. And
Yeah.
then you can see like when you multiply, this is 0.00 whatever, 0.001,
Yeah.
0.007,
Yeah. Yeah.
0.06, and all. And so this is pretty much everything is zero. So what
Yeah.
happens is then your weight metrics
The
get
last
pretty
one might be
skewed.
one, but okay. Yeah.
Yeah, no, this one, This one is 1 because it's
Yeah,
20,000.
wouldn't the 0.6 be a number?
0.6.
It doesn't matter.
No, right? It would be still, see, because we need to round off as well to the
Okay, yeah,
nearest 10. It's
okay,
an int, right? So
yeah, doesn't
then the
get round
thing,
up.
yeah. So it's like, you understand what is happening here, right?
Yeah.
So what happens is then there will be so many zeros, and because
Yeah,
this is an outlier,
yeah,
so the idea is this part is not optimal to quantize.
yes,
That's what the
yes,
idea is, right?
yeah,
Right.
yeah, yeah,
And that's the uh, so then the other part is like, then when you need to dequantize this, you need to divide it from the
a
quantization
bunch of
constant,
zeros. Yeah,
right? And
yeah,
again bunch of zeros. So
yeah,
this is the problem with usual quantization. So
yeah,
what they are saying is, if we can have some kind of a knowledge about the distribution of the weight matrix,
yeah,
we can quantize them by blocks.
yeah,
Maybe if you quantize all these outliers in a one block,
yeah,
it would be okay, right? Then you
yeah,
quantize all these tens or 20s or whatever in one
yeah,
block, it would be okay,
yeah,
because we
yeah,
can have an amazing representation. Then let's think of what is this normalization thing does.
yeah.
So yeah, I was so bad with drawing a normalization curve, so I asked one of my friend to draw this for me, which is pretty great, you know. um, yeah. Now, can you see this thing? So now what
Yes.
we do is, now we,
This
we
is
assume all our weights,
quantiles. Yeah,
yeah, all our weights are normally distributed, right?
yeah, yeah,
And then we first kind of squash this word like range, because we can always change the standard deviation, right? We can normalize them. And then
mm,
we kind of drop them in between -1 and +1,
yeah,
right?
yeah.
And then what you do is, basically you have 16 blocks,
So
right?
+1 would be the max, I guess,
Yes,
based on the standard deviation. Because if a
yeah,
standard deviation, it'll be 2, 3, 4.
yeah, because I think this is more like normalizing the weights, right? Like because we do
Scaling between
this for,
-1 and 1.
yes, like we
Like,
do for
yeah,
pixels. It's not much,
yeah,
but the idea is this blocks thing, you know.
yeah.
So the idea is, now
The quantiles.
we can, because a normally distributed curve, like
Yeah.
we can kind of divide this into uh, parts of 16, where each part from here to here number of weights is same.
Hmm.
Because
Yeah, yeah,
if you
yeah, yeah, yeah.
take the area
Versus
of this
quantiles. Yep,
part
yep, yep.
versus area of this part is
Yeah,
same,
it's the
right?
same. Yep, yep.
So this is one quantile, this is one quantile, this one, so this is pretty awesome, right?
Yep,
Because now you have bunch of weights here, bunch of
yep,
weights here, bunch of
yep,
weights here, but they are equal. So equal, and
yep.
they are like closer to each other, so you won't get into that kind of having a lot of zeros, or having a lot of big values, or whatever it is.
Yeah.
Having a lot of zeros won't be a problem, because this can handle the outliers pretty well. So then what they do is, basically they quantize each block separately. Quantize means
Hmm.
they compute the quantization constant
Yeah.
for each block separately, which is pretty cool. So 16, 15, 14, so these are blocks. So now you have 16 constants, 16
Hmm.
quantization constant separately.
Yeah.
And then you kind of keep them in the memory, like kind of this, what do you call, computational function, computation data type. So what do you do is, you kind of dequantize it with C.
Hmm.
So yeah, this is like pretty much their quantization thingy. Do you have any questions in that?
No, I understand the percentiles, I mean the quantiles,
Yeah.
and then each weight will be between negative and 1, and then for each, if it's very high, then it'll have a different number. But
So previously you just need to take one
Yeah.
quantization constant.
Yeah.
But here you have now 16 constant for each bucket
Yeah.
because you kind
Depends
of
on the C.
down.
Yeah.
Yes,
Depends on
depends on the
the
C.
C. Yes. The value of
And
the
yeah,
number. Yes.
yeah, depends on the C. Exactly, depends on the C. So because of that, because now you understand, right? You don't get that zero thingy
Yeah.
because this can scale this separately. Then this double quantization is, so you need to keep these things in memory, right? C1
Mm-hmm.
and C2. So what they're saying is, rather than keeping this in float 32 or
Yeah.
float brain
So
16,
16. Yeah.
they have again quantized these
Yeah.
values, these 16 values to 8 bits.
Yeah. Yeah.
You understand, right?
Yeah.
That's pretty
Yeah.
much double quantization, which is
Yeah.
yeah,
Yeah.
which is pretty awesome. That's pretty much the paper. So basically, you keep your LoRa weights in B float 16, and
Yeah.
then you kind of keep your model in normal float 4. But always remember,
For
they
bit.
have two types of data, that is like the storage data type and the computation data. That means during the forward propagations and backward propagation, whenever you need activations and everything to compute gradients for these LoRa layers, even any matrix multiplication, they always convert it back. So yeah, so that's pretty much the paper. And yeah, I will highly recommend you to go through this. So then we first discuss why it is important to fine tune large language models for our custom tasks. And we also discussed why it is a hard thing to do, like because we need a lot of GPU power and all. And then we also kind of summarized what is this concept of parameter efficient fine tuning, why it is important for the improvement of this area, improving this area. And then finally, we went through low rank adaptation, low rank adaptation, which is like a pretty common parameter efficient fine tuning method right now. Actually, mm, the PyTorch Lightning blog said it's like the state of the art. And then we also went through the latest paper, QLoRa, that combines quantization with their own float method, plus using LoRa. So now the last part, which is the easiest part, now you can see like how easy this is to run. So this is the notebook, the Falcon Guanaco. So basically, Guanaco is a model that if you use QLoRa, right? That's the idea. And yeah, so basically, you first need to install these libraries. This is PEFT library, and this is Accelerate, Transformers Reinforcement Learning, Datasets, Bits and Bytes. Um,
Yes.
INOPS
Synops.
is flexible and powerful tensor operation for readable and reliable code. Suppose NumPy is like a tensor operation. Of course, we need to have a lot of tensor operations. And so then you kind of load this dataset.
Mm-hmm.
It's Open Assistant Gunaku. So the idea is like it has some sort of dialogues. You can check this dataset out. Yeah, then we come to the model. So the model is like 7 billion shared brain float 16. So this is the full model. And then it is super simple. Now bits and bytes kind of support QLoRa. Of course, I think the first author of QLoRa paper is the one with the bits and byte repository. So all you need to do is you need to do a configuration. So load in 4-bit true. 4-bit quantization type is normal float 4, and 4-bit compute data. Remember computation thing, it's torch
Mm-hmm.
float 60.
Mm-hmm.
Hmm. So I don't know why they don't use the B float 16. Maybe torch float 16 means B float 16. I don't know. Something to check. And then yeah, then we have the auto model. We load the auto model, right?
Yeah.
And So then we have the model config use cache false. Maybe you don't download it for download it for cache or anything. Yeah, it's not much of a big deal. And of course tokenizers, normal thing. So then here is more like because this is a separate setup, right? This is like the quantization part, quantization
Hmm.
configurations, I would say.
Yeah.
Maybe it does the quantization here, right? Auto models from pre-train. um, Maybe the checkpoint, but it's, yeah, but the idea is this is pretty solid, this is already,
Oh, alpha is 16. What? Okay.
yeah. Yeah, this is the LoRa alpha, that scaling parameter, and this is the LoRa R, which is like the hidden size,
Yeah. Yeah.
hidden size, or like the autoencoder bottleneck layer
Yeah. Yeah.
kind of a thing. Yeah, so then this is the LoRa config, and yeah, you have a bunch of the task type we call LM, bias none, LoRa R, LoRa dropout. So these are hyperparameters, I guess. And then this is the thing. Like, remember we were talking about where to apply these things. So these are
Mm.
like
Mm.
from the paper. These are like from their
Yeah.
LoRa paper. They have applied this for dense layers and dense H to 4H,
Yeah.
4H to H, and Cori key value.
Yeah.
All these layers, and yeah, these are like their transformer layer names, and says this is really easy, so you can play around with this
Yeah.
and think what to do. And this is like SFTT trainer,
Mm.
supervised fine-tuned trainer,
Yeah.
from TRL library. What?
Transformer reinforcement learning.
Yeah, I
TRL.
think so. These are normal training layers and
Mm.
all. So this is their new optimizer,
Yeah.
page
Oh,
atom
okay.
W 32-bit.
Mm.
So that's so I think this is. Do we need CUDA kernels for a new optimizer?
It'll be
Theoretically, no need,
fast.
right?
I
Might
mean,
need, because
depends the
there's this.
speed.
Yes, because in the paper they have mentioned that they have also open source the thing, and yeah, the
Mm.
SFTT trainer and sequence length, and you just need to dump
Five.
everything
Oh,
here,
yeah.
and yeah, then finally there's this thing as well. We will also pre-process the model by upcasting the layer norms in float 32 for more stable training. Yeah, like normal, I don't know why, maybe it's from the paper. These are like, but I kind of get it, because you don't need to mess up the normalization layers usually. With normalization layers, what you do is we are adjusting the um,
Mm.
inputs and outputs. So maybe having a better precision
About 32. Mm.
would give better results. It could be the
Mm.
reason. Then you just train it. So train low. So this is pretty much it actually. Yeah.
It looks pretty straightforward. You can play around with the parameters. I don't know how that sequence length parameter affects memory
Yeah.
size. Obviously it does, but
Yeah. This is like a long discussion, and yeah. To conclude this, what do you think? Like, uh, do you kind of what do you think of Q Lorena? Is it good?
it
Like,
is quite cool, yes. And they make everything quite easy to use as well, which is more useful
yeah,
than
yeah.
a technical
Um,
contribution.
I'm actually quite amazed. Like it's pretty prompt.
No, it's a good time to be alive,
Yeah, exactly. It's a good time to be alive. Yeah, I mean,
or in the machine learning space.
yeah, exactly. I mean, this is like a good thing, like, although there are larger models and all, still there's a huge part to play. That's the main idea. And yeah, so that's pretty much it for today. And thanks a lot for joining. And we will come up with another video as soon as possible. So
Yep.
thanks a lot, Ravindu, and yeah, we will see you guys again.
No good. Yep. All the best.